Is complete.
Yeah. Am I audible, sir?
Yes, audible now.
Yeah, great. So, welcome everyone. I guess everyone has joined. Those who have not joined, we will be posting the links. Please join in fast. We would be starting, right?
Yeah, hello and welcome everyone. I'm Megha Mitra and this is Jai Bhatia. And we also have Nishka Sharma and Anushka Roy, and we are your hosts today. And also, we have our coordinator and mentor Shubhajit Chandra with us. And we'll be starting very soon. And I think we are going live, right, Jai?
Yeah, we are live. Yeah, I'll just check it out.
Yes, we are already live. We can start.
Yeah.
All right. Thank you so much. And okay, so welcome everyone. A very good morning to all of you. And today we have our inauguration program for the IITM BS Mathematics and Statistics Academic Cell. And this is quite a star-packed orientation program. As you can see in the PPT, we already have our schedule live. And so we will start with the speech of our mentor and coordinator, Shubhajit Chandra, and he will introduce ourselves to you and the core members. Sir, please take over the screen.
Yeah, thanks, Megha. So, good morning and welcome, everyone. We are very glad to have you all here. So, first of all, I will welcome JK, Sarang sir, and probably Usha ma'am is also here. So, they are joining our session. So, officially, this is the first event which we are organizing in this IIT MBS Math Stat academic cell. So we are overwhelmed with the response in the first event. The broader aim of this community is to increase collaboration between the students and faculty to build a platform where a fruitful discussion and logical reasoning can be practiced. We are planning to organize seminars and workshops to introduce members to different areas of maths and stat, which may interest them to study those in further detail. So I want to thank all the core committee members who are here and who has helped to organize this program. So they worked very hard for last few days, and I mean we are organizing this in very short notice. So they had to work along. I mean in each night they are working, that I know. So I am thanking them all. I also want to thank my colleague Shubham, Sushmita, Subhashish, Nikita, Karthik for helping me in the process of building this community. So I will not take much time because there are a lot of speeches which are coming front end. So let's go for that. Thank you. Thank you, everyone. Yeah, Jay, you can take over from here.
Yes, Mega. So this is the grand opening of the IITM BS Mathematics and Statistics cell. So how are you feeling?
Yeah, I'm feeling quite productive right now. And as we promised that this will be something to think beyond the graded assignment and activity questions, right? Like we can jump over the river of something. So the one thing I'm very much screwed up about is why so silence in the chat. So we need your interaction, guys, and we have planned that some of the best chats will get some shout out from us. And so if you want to interact, do interact in the chats, and we are also taking over the YouTube live as well. So please interact with us, and surely we will be coming back to you and give you a shout out. So as of now, we have to introduce some of our core members to you. Nishkarsh, can we please roll out the slides? Yes, so Shubhajit sir, we will be extremely glad if you can introduce these core members, and you can introduce the structure of our cell to
Yeah.
all the audience.
Okay. So we have divided our core team in some specific teams. So first is seminar and research team. So they will work on organizing seminars and organizing workshop also. So in this team there are Anuras Chatterjee, Anushka Roy, Udit Dikshit, E. Karthik, Swagata Datta, Harshit, Susnigdha Saha, Jay Bhatia. Can you just say hi to all the members?
Yeah, all the core
Yeah.
members. Yeah.
Hi, this is
So
Anush. Hi.
Anuraj,
Yeah,
are you
And
here?
this is Jay.
Yeah.
yeah, and this is Megha. So Nishkash, can we have the next slide?
Then we are planning to organize Olympiad and workshop also, as I have said. So till now in Olympiad team we have only two members, Sijita Banerjee and Swagata Datta. Are you here, Sijita and Swagata? Yeah. Okay. So in workshop team there are again Sijita Banerjee, Akhil Sharma, Shreyans Pathak, and Lihani Raj Mohanta. Yeah.
Hello,
Hi.
everyone.
Oh,
Nishkash?
hi everyone. Hi.
Yeah.
Then there is sponsor team. So in sponsor team there is Muhammad Abu Bakar Siddiqui. I think Abu is here. No? Okay. In technical team we have Karthik, Anmol, Meghna, Nachiket, Shreyans, Nishkars, and Jay.
Hello,
Yeah.
sir. Good morning, sir.
Hello. Good
Hello,
morning.
hello.
Good morning.
Hello.
And this is the overall management team. So here are Shabnam Chakraborty, Gyanaranjan Nayak, Ajit Nag, Chaitanya is there, Amitabh Roy, Meghna Chaturvedi, Parul, Nachiket, Nishkash, and Deepak. And Megha is also in the overall management team, I think.
Yeah.
Right? Yeah.
And yeah. And so that's it, guys. Thank you so much. I would wholeheartedly thank all our core members for being so much supportive and so much hardworking for making this seminar possible. And also to all the audience, we will be clearing all of your questions and queries regarding the functionalities of the cell in our evening session. As of now, here we can proceed towards our main part, right, Jay?
Sure, yes, I guess everyone would be waiting for the same.
Yeah.
So we can,
So,
yes.
yeah, of course.
First of all, I would like everyone to just switch on their cameras for a lively interaction. We would like to see you all, interact with you. So it would be great if everyone is visible, right?
Yeah,
Yes, Mega.
and also we would definitely love to hear your opinion in the chats. And as we said, the best of the chats will get a shout out from us, and we will read it out. And also, okay, let us now move on to the best part. We will be very happy to invite our faculties, and here we are inviting Professor Sarang S. Sane to give the introductory speech, and to all of our audience. And yeah, we are very blessed to have you here, sir.
Hello. Yeah, thanks for having me here. So, yeah, I'm very happy to be here and to see that there's a large number of people here who seem to be interested in this maths and statistics academic cell. Uh, so, as far as I understand, the functionality of the cell is to organize workshops and activities related to mathematics and statistics. And so, this will be a community of people who are dedicated to learning mathematics and statistics beyond what you have learned already in the data science program. So possibly more detailed topics beyond what you learn in Maths 1 and Maths 2. And that's very nice to know. So as a professional working mathematician, it's very heartening to see that there's a large response for such an activity, and I wish the cell the very best. So I think there was an informal session before this, meaning a few months ago, which was not part of the cell, but sort of some loosener where I also gave a talk. And I hope that there'll be many interesting talks, which are much better than the one that I gave, and which will even sort of bring you towards some of the current research in mathematics. And like all of you, I'm also waiting for Professor Saket Saurabh's talk, which is at 12, and Professor Ritubroto Munchi's talk, which is in the evening today. So I hope all of you will continue and be there. Both of them are very well-known academics and really sort of leaders in their respective fields, and extremely bright and talented scientists. Yeah, so I wish the cell the very best, and I hope to be part of any uh, sort of workshops and so on that you organize to hear more uh, from various speakers. Yeah, thank you. Yeah, you can take over whoever's.
Thank you so much, sir. Thank you for your kind words, and we are very happy to have you here today. As we students know that whenever we ask for a favorite mathematics faculty, it is always Sarang Sane, right? And we are very encouraged to hear your words here. And as sir said that it is this sale is something beyond our curriculum, our course curriculum. It is about diving deep into mathematics, just find some gems from it. So thank you so much, sir, for your kind words. And here we are moving on to the next part, where we are very happy to have Professor Usha Mohan ma'am within us. And whenever it comes about statistics, the only name we know is Professor Usha Mohan, right? So, ma'am, you can take over the screen. It's all yours. Hello. Technical team, can you please see if there is any glitches Usha ma'am is facing? We are extremely sorry, guys, because there are technicalities. There will be some technicalities. There will be some fault in the technicalities. So we have to wait a little bit to hear some words from Usha ma'am. I think she is here and she will be joining us very soon. We are extremely sorry, guys, as Usha ma'am has to handle such, naughty students like us. She is facing actually a lot of difficulties to join here, and we can expect that she will be joining us very soon. But yeah, as of now, we don't want to disappoint you. We have such lineup of great treasures for you already. So here we are going up with the speeches from our own instructors, and we can call them very proudly our own because they actually the one who mentors us for these courses, and they're always ready to clear our doubts, always ready to guide us towards being a better person. So here we have our instructors. Nishkash, please roll on the slides.
Also, Mega, not just the academics, overall development of a personality. They are such supportive, you know.
Absolutely.
In few days I've experienced a lot. The support, the immense support, the guidance. It is just a blessing to us, I guess.
Of course, of course. So, audience in the chat, can we have some, gratitude towards our great instructors? We will be very happy, and we will be reading out the chats loud, which we like. So here we are very happy to invite Dr. Shushmita P, who's the instructor for mathematics, and we have seen her quite a lot of times in the live sessions and everywhere. And we are very happy to have you, ma'am, and we are very keen to hear your words. Please take over the screen.
Thank you, Megha. And hello, hi everyone. So it's really nice to have a math and stat cell. Yeah, this is something that we wouldn't have imagined a few terms back. So thanks to Shubhajit for all the work that he has put in to bring this cell up, and not just to Shubhajit, to everyone who is a part of this and who has been behind this, and to all the very enthusiastic students, that learners actually, that all of you are putting the effort that you're putting in is clearly visible. And yeah, I hope that not just as you all already mentioned, not just studying math 1, math 2, stat 1 and stat 2 as a part of the course just for the sake of studying it. You're all I hope this cell will make you all more enthusiastic towards studying maths and statistics beyond these 4 courses. And all the very best to the team, and we are always there for you. Megha, you can take over. Thank you for the opportunity to talk.
Oops.
Thank you very much, ma'am. It was an honor to hear from you. Yes, Mega. So who is coming next?
Yeah, I can see that you are very excited. But as of now,
Yeah.
I would love to hand over the mic to Anushka. She is also one of the core members of our team. And Anushka will, I'm totally in surprise. Okay, Anushka knows who's the next speaker for us. So, Anushka, can you take over?
Yeah, sure. A very good morning to everyone. Maths, as we all are coming from different types of backgrounds. Someone is coming from engineering background, someone is coming from pure maths background, or many other different things. But one very important thing, or one very colloquial thing that we always heard about is maths is the language of science. We always heard that during our school days, and even when we grow up. But very few of us actually study stats. But according to me, if maths is the language of science, then statistics are the grammars of these languages. And here we, the IITM BS Maths and Stat Academic Cell, are here to collectively explore your interest in the field of maths and stats. As a famous saying goes on, facts are stubborn, but statistics are more pliable. So just let's take a stance and from transforming us into pure maths and stat pursuing individuals and explore our interest in the fields. Our professors and our PODs are there to support us always. The academic cell is here to be another support in the transformation process. Let's come together, analyze our interests collectively, and look forward to span our interests in the maths and stat field. Thank you so much.
Thank you so much, Anushka. That was like some great insights from you. Yeah, we do agree on that part. And so I'm very happy to invite our next speaker, who is also an instructor from the Python Introduction to Python course. And we all know him. He's very spontaneous. He's very lively, Mr. Karthik Tyagarajan. And as far as I have known Karthik sir, he is very interested and always talking about popular maths. He's very interested for popularizing the maths, and even we had our previous workshop. He was interacting with the students, and what I could see is the students love him very much. Like, he is the people's instructor. So here we invite Karthik Tyagarajan sir. Sir, you can please take over the screen.
Thanks a lot, Megha. So I'll just turn on my video. Is there any way I can share my screen? Is that fine?
Yeah, we are looking into that, sir.
So I think it allows me to share. So shall I go ahead and share?
Yes, sir. You can go on.
Okay. So see, I'm like so used to having something in front of me while talking that I had to create some slides. So I apologize for having something in front of me. So I'll just make it very brief. So very happy to be here. Thanks to Subhajit for this wonderful opportunity. I think Subhajit and team of core members have put in a lot of work. So I'll just give some context for why this cell is very important in my opinion. So if you look at the subjects in our program, right, I've just listed down some of the diploma subjects here. They're all, most of them have some connection with math, right? So if you have Max 1, Max 2, Stats 1, Stats 2, they're obviously math subjects. And I jokingly tell Shubhajit whenever we get to chat that machine learning subjects, which we typically think of as computer science, core computer science subjects, for all those math enthusiasts out there, they are just applied mathematics subjects. So I've just given, I'm just showing one example of a problem that we tackle in this machine learning techniques course, which is if you don't know the name of the subject, ideally what you would think is we are doing some kind of an optimization course, right? So that shows how important mathematics is and statistics are for this program. So if you look at the courses that are listed down here, I've just taken up one diploma, right? 50% of the courses, about 6 courses, are either pure math or some kind of applied math, right? So this is what is necessary for any student of the program to master. Okay, so these are in some sense the necessary conditions that everyone has to go through. But that said, the question that we have to ask is that math that we do sufficient, right? So I would say that it's not sufficient, especially for those of us who like math, right? So the big problem is we tend to treat mathematics as a means to an end, right? So okay, I have to do mathematics I have to do these 6 courses so that I can get the degree. But learning doesn't end with that. So learning is often conflated with getting a degree, getting good marks, right? Especially bonus marks, right? I don't know how many of you remember 2 terms back there was this concept of bonus marks, and we all saw what happened, right? So there must be some endeavor from our side, right? From the instructors, faculty, and the students, where we go beyond marks, grades, and engage with the subject in a more meaningful fashion, right? So I think for all of us here, mathematics is an end in itself, which is a very important thing, right? So it's not just something that you do, get some grades and move on. So I think the cell will satisfy that particular requirement. Second thing which I feel the cell will do is it will decouple learning and exams, right? So there is a life beyond exams. I hope that will happen. And finally, I hope it will also couple learning with discovery, right? So how do you discover mathematics? I hope all the workshops, the research endeavors, all these will cater to that need. There is also a lot of fun associated with it, right? So we have some fun activities planned, and I hope the cell will, over the course of its existence, cater to that as well. And finally, there's also some meaningful frustration that's involved in mathematics, right? I think we all know that. I hope we'll give some vent to that as well, right? So my best wishes to the cell. I'll also try to be as much an active member of the cell as possible. Finally, yeah, thanking Subhajit and team for putting up such a great show, right? So best wishes. That's it from my side. Thanks, Megha. Yeah, can carry.
Thank you so much, Karthik sir. Your presence and your words has always been a kick up for us, always. And as I said, you are the people's instructor. Everyone loves you so much. So, Jai, would you like to take over and thank Karthik sir from our behalf?
Yes, definitely. The presentation from sir was putting a great insight, and also I was just seeing the chat that someone said, yeah, Siddharth was saying that 18 years of learning maths, and he was learning it for grades, and now is here to go beyond the grades. So this is what makes it interesting. Their guidance make us think that how we should procreate these things in our lives to make it more meaningful, just going beyond the grades to do something good. Yeah.
Yes, and I would like to give a shout out to Priti as well. She has said that extremely awesome lectures explained nicely. Apart from lectures, interactive sessions are very much helpful to understand the course. The whole structure of the course is simply awesome beyond imagination. I never thought before joining that it will be so much supportive. After joining, I felt it to be more accessible than the offline courses. Thank you so much, Priti, for your feedback. It means a lot to us. Now we are moving on to a very special session. One person whom we always love to hear from, and that is Jai Krishnan sir himself. And we know how much we love him, how much we love to hear from him. So Jai Krishnan sir, we are awaiting. Please take over the screen. Sir, are you here with us?
Yeah.
Yes, sir.
Are you able to see me?
Yes, absolutely, sir.
Yeah. Okay. So, I mean, first of all,
You are not audible, sir.
Yeah, sir, I think there are some problems with the mic.
Okay.
Yeah, it is good now. It is good.
Is it now?
Yeah, it is good now, sir.
Okay. Okay. Perfect. Yeah. So, first of all, a big congratulations to the entire members. I mean, not just the organizing members, but also the initial members of this club. I mean, yes. I mean, I see that you have written it as mathematics and statistics. And yesterday I was just messaging Shubhajit that it should have been statistics and math club. So, which academic cell, which is basically SMAC, right? I mean, it sounds so Gen Z when you have a funny acronym, and which would make it. I mean, it makes it smacky and make both math and stat more consumable, more delighted. Like what Karthik said, I think the purpose of math and stat is not just to what do you say, uh, get marks out of it, right? I mean, doing a calculus problem or finding the basis, the subspaces. It should not be limited to some 14 questions that you try to. I mean, I don't know what your strategies are. I think I've heard strategies that people take up additional courses so that they can get more time for writing maths too. So, I mean, that is not the whole purpose of math and stat. I think math and stat is a language in itself. It should have its own. I mean, I'm not expecting everyone to do like fantastic. I mean, it's not about the marks. It's also about the fun, the enjoyment, and I think the entire school education has. I mean, somebody recently had commented to me that the detrimental psychological effect of mathematics education in schools has made almost 4 billion learners hate math. And I mean, he was talking about practically the entire school children across the world, not just India. So I hope, so a couple of things. One, like what Karthik said, I think it is important that you understand that mathematics and statistics go beyond what is taught in academic curriculum. But more importantly, the way I see it from a program perspective, it is I see this as a very good student-led initiative, student and instructor-led initiative. I think we have been trying hard for that right from year one. I mean, all these are attempts, and what you should really try to do is make sure there are these initial activities like these where you have talks, workshops, and other things. The moment you are able to stabilize it over 3 terms, I'm pretty sure that this will sustain. So make sure that you target one activity each term. I mean, all the support from our side would be there. We want more people to enjoy mathematics beyond the curriculum, and we would also want more students. I mean, this should be like a flagship cell which tells us how to conduct student activities, how to motivate student activities, and yeah, I mean, you all of you would be pioneers as far as the program is concerned. There are a lot of such student cells. We have the entrepreneurship cell, the music society, sports cell, everything is coming up. It is fantastic to see that in this online medium, we are able to create both academic as well as extracurricular activities. And I hope all of you would contribute to the larger program, provide some models that we could even tell others, world outside, about what our online program is doing. I mean, I wouldn't say online program delivered online is doing, so that I mean, all of the world can actually learn from us. So kudos to everyone, and I'm also keenly looking forward to the 2 lectures. I mean, I saw the names and I was like, okay, I will not, I mean, make myself stand between both of them. So yeah, go ahead. All the best, everyone. Looking forward to a lot of interactive and more learning sessions in the months to come. Thank you.
Thank you so much, sir. And as we were talking, we could see how people were reacting in the chats. Everyone just loves to hear from you. And thank you so much for being with us today. So here, I would call Jay and Anushka to read some of the. I think we have a lot of funny chats pending up. Can you
Yes,
just give some shout out?
definitely, Megha. I was just looking through some of them, and a few pointed out that they fear of maths because while having the experience in JE or solving some calculus. So this is what, this is where we are coming up, to make maths interesting, to know some interesting facts, to know what are the applications, how core mathematics is so good. And maths is applied each and you need these things, as Sir Karthik sir also pointed out through the slides, that how important is maths, definitely for this course, and not just for this course, beyond this. So yes, please do join us. It would be, as sir rightly said, that this team would be the, the pioneer. The members here are the pioneer of this. So we are going to have a wonderful journey, and also we have planned many things, right, Mega, from seminars, Olympiads, workshop. I guess I should not reveal much of them.
No, no, we
Much
will
is
be
coming
reviewing
up.
that in the evening sessions. And also, I
Right.
would like to point out one thing that Jay Krishnan sir told us. It is a hack that we all use. That is using taking additional courses just because we have more time to write the papers of maths. So I want you all the audience to admit who many of you have done this hack to take additional courses just to get more time to write the papers of stat and maths. Okay, just admit in the chat. And here we are very happy that we finally have Usha ma'am among us. Ma'am, we have been waiting for you so long. In the chat, people are always finding where is Usha ma'am, where is Usha ma'am. So here we have Usha ma'am, the wizard of statistics. Ma'am, we are very happy to have you here. Please take over the screen.
Yes, I'm no wizard of statistics. Okay. Good to see all of you here. Am I audible?
Yes,
Can you
Yes,
hear me?
ma'am. Yes, ma'am.
I see so many people here on a weekend. Here it's raining in Chennai. And I'd like to correct all of you. I'm no wizard of statistics. If anything, I'm trying to initiate you people into the world of statistics. And if I have done that, I feel I have achieved my objective. Okay. Nothing much to say. I just wish you all continue with your passion. First of all, do not only math or stat, whatever, if you have a passion to learn I think no matter how difficult it is, you will learn it. That's it. Okay. So I think that is what you all should learn is, and never sort of be scared of asking a question. You all might think it is a very silly question, but mind you, most of the answers would come only from silly questions. The minute you start accepting everything a teacher says as gospel truth, okay, you lose your ability to think. That's what I would try to say. And always try and understand, be it the best teacher or the best book. I think all the thing you need to understand is reason it out. There is a reason for why people have written such mote books. Okay, it's not that they had nothing else to do. There's a reason. So, can you remove this from the screen? I don't want to keep seeing my photo. Have something better, right? Thank you. Okay, so I think it's wonderful that I feel very fortunate that I'm a part of this program, and if it has helped people, I feel even more blessed. I wish you all the best, and I really hope that this program can reach out to as many as possible, and we continuously look for feedback. You all should again, you should actually actively give feedback in a positive way. Please let us know how we can improve this program, how can this help, and how can this reach out to many more. Okay, wish you all the best. Thank you. I'll be here for some time. Thank you again for giving me this opportunity to meet you all. It was, I'm very bad at making speeches. I prefer to teach rather than speak. So, wish you all the best. Thank you.
Thank you very much, ma'am. It was an honor to hear from you. And yes, personally from my side, Megha, do you know, I just record my that old. Currently in the diplomas. I record some days my foundation level when I was preparing for my that clearance exam, and I was studying from ma'am. And meeting her now, it is a great honor, and I feel really excited. Thank you very much, ma'am, for that wonderful words. And as ma'am spotted out that she likes to teach rather than making speeches, you know, uh, really excited to learn from you a lot of things. Thank you very much, ma'am. Mega, what do you feel?
Actually, I think she is facing some glitches, so we can carry on.
Yeah, Anushka, please. Yes, Anushka, sure. Can you please share the screen?
Actually, we can see many interesting chats up here.
Oh yes, I also saw that the idea of Smack was, really everyone felt it so interesting. I saw some chats coming out for that chat. That word Smack.
Yeah, Janvi was saying he was scared of maths because of J, but now she is loving it, and it's a great news for us that because of these things, because of these cell and because of this program, someone is loving maths after overcoming the fear of it.
One more chat says, Usha ma'am, thank you for making statistics so simple. The way you bring simple to complex journey of concepts is simply awesome. Unknowingly, we reach to solve the complex questions in a smoother manner. One of the favorite professor, Usha ma'am. Thank you. Yes, ma'am. So there are a lot of feedbacks, a lot of thankful messages from you. Yes, learning from you is a great experience, ma'am. Thank you. Thank you very much for that. Yeah, somebody is also sharing some insights of the paradox, the May event.
Now we can call up to Shubham sir. Can we have Shubham
Yes.
sir amongst us?
Absolutely. And very sorry, guys. I just lost connection because of the network. Like we all know what is the situation in Chennai right now, and I'm very happy that we have so many people even in this situation, right? So here, Nishkash, can you please roll out the slide?
Yeah, till that, I guess Mega, Cyclo, and Rains also want to participate in the program.
Why not? Yeah, of course. And
Yeah.
we have here Shubham Maurya sir. He's the instructor of mathematics, a very lively, very spontaneous person. We all love him. And yeah, Shubham sir, we are very happy to have you here. Please take over the screen, sir.
Uh, Thank you so much, Megha. Thank you so much, Anushka. Uh, so first of all, giving the congratulations to all of you to making such a cell, to be making a growth or maybe in improving a combination of mathematics and statics. So, and thank you so much for Subhajit and the you people core team making a such cell. So today's I have a remember when I was in a starting of like when I was in 11, 12. So I was very confused with the terms when I started studying mathematics. Like I have seen such some words like theorems, proofs, word lemmas, corollaries, proposition. So when I was in the starting, I was a bit confused with such word. So today I will I will give something about like talking about what is the lemmas. Like I am from mathematics, I did master from mathematics. So now somewhat I comfort to knowing these words. So uh, so like the first thing is when I was in starting. So the first word is like a definition, saying to be the definition. So in the definition is nothing but an explanation of mathematical meaning of a word. So when like and the next word is the theorem. The theorem is when I was in starting uh, mathematics. Theorem when I see is the word theorem and written some lines, I got scared. So, but yeah, now I something know that okay, theorems are nothing but a statement that has been proven to be. So, like you, all of you know that the Pythagoras theorem. So, and like another word is the lemma. Lemma in mathematics is generally used word. Lemma. What is the lemma? So, lemma is a true statement which used to be help to proving a true statement. Generally, you can say used to help in proving the theorem. So these are the some words, and similarly there is another word corollary. So corollary is a statement that is simply deducted from a theorem or a proposition that is you can say result
I
of
have to tell
some theorem.
Saket sir because he is not here yet. And so Sarang sir has texted that to give 5 minutes break before Saket sir talk.
Sorry, am I audible? Megha?
Yes, sir, you're
Yes, sir.
audible.
Yes, sir. Yes, sir.
Okay, so so there is another word like I mean in starting the word is conjecture. The conjecture is a statement believing to be true, but for which we don't have proof. So, like there is a conjecture, you can say there is a point that doesn't lie. There is a point that doesn't lie on any line. Such kind of like such a statement or such something we have that we don't know proof, but yeah, those statement to be believing to be true. So there are some words. There are many more words which I used to be confused when I was in starting when I started in mathematics, doing something in mathematics. Yeah, I started loving when I was in 11, 12 when I got when I started studying the calculus portion, uh, limit continuity. I got more interesting in mathematics. So so this cell is a part of this mathematics and statics. So I thought maybe these words may be uh, going to be an interesting. And yeah, that's the closing my word. Thank you so much for making us such a cell, and congratulations to all of you for making this cell.
Thank you very much, sir. It was great hearing from you, and yes, we look forward to learning a lot of things by being a part of the cell and also being in the program. Uh, so, yeah, I see something interesting coming up in the chat. Anushka, can you please tell us?
Yeah, sure. Or Ritik Roshan Maurya said something interesting. Lemma is the online feature of India. It's really very interesting.
Yeah, I also saw one chat that what is the probability of rain hitting Mega's connection again. So I hope it tends to zero. We don't want much interrupts. Also, we have some questions in the chat that what is the motive of the session. Guys, please be with us. You'll come to know as and when you move forward with the session. So yes, please wait. You know,
Many surprises are coming for all of you, and I'm sure you'll be
definitely,
loving it.
definitely. Also, before Sir joins, we would like to take a short break of 5 minutes. So yes, everyone in the chat, it's your turn now. Anyone would like to share their words?
Yes, Ritik, conjecture is indeed the best online course.
Truly said, truly said. So yeah, I would be looking in the chat. Come on, guys. What would you like to share?
We also want to hear your views about maths and stat. Please speak up.
Yeah.
Just take the
Also,
chance.
Biswajit says that do we have any WhatsApp or Telegram group? No, Biswajit, we are not having any Telegram group or so. We have the Google groups. Uh, Also, the joining rollout form will be released soon. For more information, that would be shared in the same seminar. So yeah, please stay tuned.
Sir, can I say?
Yes, please.
It's a bit.
Sure.
Yeah, for me, math is like a play. When a kid starts playing, then only he or she will learn. If you are looking for the subject, then you will never learn. So start playing with numbers and enjoy it. Then only we can learn the stats and probability stats also. For me, it's just a play only.
That sounds very interesting, isn't it?
Yeah, playing with numbers. The first chapter I recover from our 10th March chapter,
Our,
right?
yeah,
Playing with
Yes,
numbers.
yes.
childhood
And
book.
yes, at that time I didn't realize that this playing would go so far and in such an interesting way that would have, such great insights.
Absolutely. And I would like to say very sorry for the interruption part. And two things that went very bad on this day of seminar is one is the weather and other is my connectivity. So I'm very sorry, guys, for that part. Okay, so as of now, we have our prime time. That is the speech of Dr. Saket Saurabh. He will be within us in a few minutes. But till then, this time, this 5 minutes, we have declared it. I remember when we were talking among ourselves, we declared it as a hypothetical coffee break where you can take a hypothetical coffee break in your own house and just wait for Saket sir to arrive. And meanwhile, we'll just interact with you guys. Yeah, guys, take on.
Hi, I am a foundational student and can anyone hear me?
Yeah, you're audible.
Yes,
Yeah,
Ravi, please.
I have an quiz too coming up, and I would like to find out a way to clear my doubts outside of doubt sessions in maths too and stats too. Is there any way possible to clear my doubts outside of just those doubt sessions?
Yes, I guess Sir and everyone is here, but yeah, someone is also coming up in the chat that we have our discourse forum, also the study rooms.
Yeah,
So
also we
yes,
have
there are
something
numerous ways.
mentorship, something.
Is it probably possible if I get a like into a Google Meet or like one-on-one with any like faculty that is
Sure,
Yeah,
sure. Sure, Hari. We will be, please wait till our evening session. In our evening session from 7 to 8 p.m., we will be coming up with all of your queries and everything. We will be interacting with you, and we will solve every query that you have and provide you with the required links. Okay. But as of guys, now can we have a big shout out because Saket Saurabh has just joined us. Clap, clap, clap. Yeah, so can we have a big welcome for sir? Everyone, you guys can turn on your camera, unmute yourself, and just take over the chat and welcome sir here. Hello, sir. We are very happy to have you here today.
I'm also very happy to be here.
Thank you so much, sir. As we know, we all know Saket, sir. We all have seen him in multiple conferences. We have seen him taking, the most prestigious prize for science in India. And I have seen till the first day we announced your name, people were just going crazy that, oh my God, we have Saket, sir here. We'll be joining the meet. And here you have, sir, the base audience that are very interested and earnest to hear you talk. So, sir, please take over the screen. We are waiting for you.
Can I try to share my slides?
Yeah, sure, sir. Sure, sir.
Try. So to share, I need to do what?
Yes, sir. The technical team will be helping you out. Nishkash, can you please look at it?
Yes, sir. Just
If you can share your screen and please show sir what is the procedure to share his screen.
sure. Nishkash. Sir, am I audible? Saket, sir?
Yes, Jay, I think you're audible.
Yeah, I guess sir just lost the connection, I guess.
That's an issue today. I mean, I'm very happy that people are still holding on even in this weather.
Come on, Mega, that we are waiting for Saket sir. Come on. The name itself will make all the things happen.
Also, Sarang sir and Usha ma'am is here, and we know what kind of a fan base they both have.
Definitely, saw it in the paradox itself, right, Mega?
Exactly, exactly.
Is my slides
Yes.
visible now?
Absolutely, sir.
Okay,
Thank you so
great.
much.
So you will let me know when to start and then I can start.
We are ready to hear your words, sir.
Okay.
Yes, sir, please.
So it's 12 o'clock, precise 12 o'clock. So first of all, thanks a lot for inviting me. It was just 3 days before the event. So expecting me to prepare a new set of talk or slides was out of the window. So I tried to, come up with a talk, which some of you might like. I have tried to keep it at much more basic level, thinking that you people have just graduated from +2. So the theme of the talk was, this was pre-decided, at least this is what was told to me, is that it is about either motivating students on studying higher mathematics, and then second, research topics of mathematics of recent times. Okay, so what I've tried to kind of mix both of these topics and tell you something. But I was also a bit surprised that, like you people are math student and, like I'm a computer scientist, why have been invited? But then I realized that the kind of computer science that I do is a part of mathematics. So at least I'll try to give you some motivation or some sense of, what this mathematics of computing is in this talk or speech, whatever you want to call it. Okay. And how did I got motivated into this topic? Because I did my undergraduate from Chennai Mathematical Institute, and where I was doing a BS in mathematical sciences rather than pure mathematics. So apart from lots of pure maths courses, we also had lots of computer science courses, which was basically theory of computing courses like algorithms, theory of computation. And that is what led me to see this interplay of mathematics and computer science, or maths and computing. And I decided to tell you a little bit about that aspects of maths and computing, and hopefully you will feel motivated at the end to go and do some of these things. For example, I'm sure all of you people have heard about what you call machine learning. Machine learning, after all, you're doing maths and statistics. So how machine learning, maths, computing, and everything that we are talking about computation nowadays fits in is what I plan to speak about. Okay. Okay. So here is the definition of algorithm. So what is an algorithm? Because this talk is about algorithms, so I thought that maybe I will tell you at least the first basic definition of an algorithm, which I found on internet. So what is this? It's a process or set of rules to be followed in calculations or other problem solving operation, especially by a computer. Okay. Now, so this is a basic algorithm. So this is what the basic definition of algorithm is. You have, all of you follow algorithm in your life all the time. Can one person tell me one example of an algorithm? I'm sure you can unmute yourself, so feel free, right? In your life, I'm not talking about algorithm. Yes, how to make a tea. Anything else? How to dress, right? We dress in a particular way. We don't put one cloth before that, and so there are some set of rules that we follow, and that is what algorithm is. So algorithm is, yes.
So, sir, discipline is an algorithm.
Yeah, discipline is an algorithm. Perfectly valid example. You go around on the road or traffic, people are driving cars and everything. Yes. So as Amit says, from waking up to everything is an algorithm. Okay. So now we all understand what algorithm is. Okay. But let's try to formalize algorithm. How many of you have done programming of some sort in your life? Yeah, DNA replication. People are going crazy. So I'm sure many of you have seen some sort of programming in your life, in your high school or even now. Programming is a great set of skill to have even when doing pure mathematics. Sometimes I like programming because, some of the small conjectures or some of the small hypotheses I have, I want to check those hypotheses. I want to check those, conjectures. I write small program and try to see how it behaves on small examples, small graphs, and things of that nature. And yeah, and that helps me to understand whether to find a small counterexample which I am not able to find by hand, right? Or it shows me some pattern which I try to use that pattern to give a formal proof to my mathematical statement, right? So this is why programming as a tool, as an assistance to our mathematical thinking is also an important art. Okay, but how do computers think actually? Okay, so here there are numbers like in an array or in some cells, and these are the top in the blue things. What you see are the numbers, and what I have written is the cell number in this, and our task is which box holds the smallest number. And how does computer work? So the computer will work as follows. It has a pointer, or it has pointer at the first cell of this, and it sees what it is storing. It is storing a number, smallest number it has seen so far, and what is the ID of box with the smallest number, because at the end it has to return. So all that computers is about keeping the ID of the place which holds everything. Someone is saying binary search. My God. No, you can't do binary search here. Think about it, why you can't do binary search here. Okay?
It's unsorted.
That's right. It's an unsorted array, right? So you can't do binary search. And so if you're going to search how VIT, someone asked some question. Okay, let me see. Okay, quick search. Okay, this is reminding me of the course. Okay, sort the list. Yeah, sort the list too much. Okay, okay. But here's my small algorithm, right? So I just keep a number, smallest so far, and ID of the box with the smallest. So currently it sees 14, and then a 1, then it moves 15 up to ID still is 15, but then it goes at 6 and it changes it. The smallest so far is 6 and ID of the box with the smallest is 3. Okay, so on, so forth. Then it finds 2 and it will change. Right? So this is how the computer thinks. It goes in a particular way, looks at the IDs and keeps it. So it is all about keeping things in a particular way, a particular frame of algorithm. So the algorithm that we saw just now was an algorithm to find the smallest number among an array. How many comparison did we do? If we had 1, 2, 3, 4, 5, 6, 7, 8, 9, how many numbers did we compare with each other?
9.
8. First one we never compared. We just kept it. Okay. Now, if I gave you this 9 size array, but you don't see the number, okay? You don't see these numbers appearing. And can you do it in 6 comparison? If I did not show you these numbers and I say, hey, can you find me the smallest number in 6 comparison? Do you think it is possible to do? You are blind, right? You can only ask me the following question, right? Is my current number smallest than this or not? That's all that you will see, right? And I will tell you answer. No, yes, it is or it is not, right?
Sir, we can arrange it, sort it in ascending order, and then in one comparison we can.
Yeah, but like sorting is going to take you much more time, much more comparison. So we will not go there. Okay, you can prove mathematically that imagine yourself that you have been given a 9 numbers and you want to compare. So if you are doing in 6 comparison, there are some cells like intuitively you are not going to ask at all any question, right? And the questions you are not going to ask, I can find a number which is consistent with all your answers and change it, right? So if you do not ask me 8 comparison, right, the cell or the number which you are not going to ask me question about, I can change that question, I can change that number in a way that you can't answer correctly, which means you can prove mathematically that you need at least 8 comparisons. So this is what mathematics of computer science is. It is not only about finding an algorithm, also finding what is the best we can do, and if something we have done, why this is the best, right? Is there a mathematical proof to say that we cannot do better than what we did before, right? So this is what the analysis, this is where the mathematics comes into play in computer science or in math, in the world of computing, right? So the program you write, it gives you a correct answer. So the first question that we ask, why is it giving me correct answer? Like, why is it not an input on which it will not give me a wrong answer? So that is where I need maths number 1. Second, I found a procedure. The procedure takes some amount of time. Okay, we have to quantify what times means, but whatever that means, it takes some time. Then the second question I will ask, okay, can I be a bit more smarter? Can I be a bit more faster? Right? That's again a maths question. Or is it absolutely not possible to show something cannot be done? Right? That's another maths question. So in mathematics, there is nothing called ambiguous. We have a mathematical statement. This is possible or this is not possible. And we try to find answers to possibilities as well as impossibility in a right way. Okay? So is that idea clear? Why and how maths enters even computer science. Even for small things like this, I give you 9 numbers and I say, hey, I will give you any 9 number, right? Any 9. I will not tell you what numbers they are, but can you find me the smallest of them in less than 8 comparison? The answer will be no, because based on what 6 or 7 query you will ask, I can come up with an array that with some number that if you do not ask me that number, that is the number that will hold the smallest of all. But you did not ask me, so of course you will make a mistake, right? So it's an intuition that I try to give you. But we can also mathematically phrase this, frame this, and put it and show to you that this is not possible. Okay? Okay, all is good? We are going good up until now? Okay, great.
Yes, sir.
So okay, but now let's try to see. Computers are fast, we know that, but not that fast. Let's see. So computers typically at this point of time can do these many operations. Let's see how many of them are. $10 crore operations per second, okay? This is what they can do. Computers can do 10 crore operations per second. Now let's ask ourselves a question. How tall is the tallest person in Chennai? Okay, suppose there were like 2,50,000, 25, yeah, around 25 lakh people in Chennai. Then our machine will take around roughly 0.05 seconds to find this. Okay. Now, if I ask you how tall is the tallest person in the world, there are like roughly 7.6 billion people in the world, and it's going to take roughly 76 seconds to find this, right? Even to find the smallest or the tallest person in the world, right? Our computers, which are so fast, are going to take 76 seconds. Okay, is it really fast? Now, do you really think it's very fast? That it can take
scale,
yes?
With scale, the answer is becoming no. Like as the scale of the input is increasing.
Yes. So the scale of input, all I am interested in is finding the tallest person in the world. Okay, just 1 second. The fun of giving talk from the home. Okay. So we talked about the scale, we talked about everything. Okay. So now there are 2 questions. What do we want the computers to do? And how should the computer do this? Okay. You understand? So like what kind of questions do we want computers to solve? And how should the computers do this? Now, is this an elephant? Is this an elephant? Or is this an elephant? So what do you think this? So this slides on elephant we are trying to convey is that you need to give computer a well-defined problem. Okay, right? So like elephant is the example of a problem that isn't well-defined. Like what do you mean? All these are 3 are elephant, but one is like picture, one is like hand drawing, one is a real image of an elephant, right? So are we talking about elephant image of a real elephant, image made by an artist, image made by a cartoon? So it's not clear what kind of questions do you ask to your computer. So it is important to talk and give your computer a well-defined question. And this is where algorithms and complexity comes, right? What is an algorithms and complexity is like, what do we want the computers to do? Today, we will only talk about well-defined questions, right? For which we can very properly say, this is yes or this is no, right? And how should the computers do this? And it is even possible for computer to do this task. It is even possible for these computers to do this work, right? So these are the couple of questions that we will try to address at a meta level today. So the first thing that I'm going to talk about is graphs. Okay. So what are graphs? Basically, graphs are some nodes, and you put an edge between them. You put an edge between these two if you want to find a relation. So this is a graph. Okay. So what these big bulbs are called nodes, and the line joining these two nodes are called edges. Okay. So I must, like, if you have seen BSMS courses, you must have seen relations and this and that. So graphs are picturesque, or the, like a picture way to represent relations. So you can think of these nodes as vertices and edges as the relation between those two things. For example, imagine that you are 10 friends, right? Then these nodes are 10 friends. And if two or 10 people, if two of them are friends, I put an edge between them. So this can represent a friendship graph, right? Or author, I mean, these are the papers. If they have a common author between them, then I put an edge between them. So graphs can help you represent several things, or you can have a, even if you are in an industry or company, graphs can represent like bosses, then the people below him, the people below him. And so you can have a hierarchical structure, and that hierarchical structure can also be represented by graph. But the best way, or the simplest way to think of graphs as an example, is that think of these nodes as people, and if two people are friends, I put an edge between them. Okay, so these are basically graphs. Or if you're a mathematically inclined person, think of this like abstractly. There are some vertices and some edges. What is edges? Is a subset of vertex times vertex. So V cross V, right? Or so whatever it is. Okay, so is the definition of graphs clear, or should I repeat? Is there anyone who wants me to repeat the definition of graph? Okay, clear. Okay, so let's follow a protocol. If something is clear to you, put +1. If something is not clear, you put -1. So maybe this way we can have a proper communication between them. That's great. Okay. Okay, so what are graphs? So graphs has some nodes and some edges. What are nodes? Nodes are these like red, these circles. And what are edges? A line joining between them is edges. So these are also useful in representing relation. Okay, let's make our first. Okay, so here's my task. What is my task? Very simple task. I want to color the vertices red or blue such that all edges have different colored endpoints. Is the question clear to all of you, right? I want to color the vertices with red color or blue color. But what is the constraint? The constraint is, if you look at any edge, that should not be monochromatic. Like, for example, I cannot assign this vertex as well as, like, I cannot assign the endpoints of an edge same color. So endpoints of an edge cannot be both red or both blue. If you look at any edge, one endpoint should be red, other endpoint should be blue. So that's a task which I have assigned to my problem. What's the problem? My algorithm is going to take a graph, and the task is, can you assign? Yes, you're right. No two directly connected nodes has this. Okay, so let's start coloring. So I assigned the first vertex. It can get any red or green. It does not red or blue. So I gave it red. What do you think? Does it forces does it forces something to get blue? Okay. So if you notice, this automatically means that these guys must get blue, because this cannot be assigned red, this cannot be assigned red. But now, what do these two red forces? It forces that all its neighbors, right? All the nodes which are assigned directly with this blue must get red. So it forces us to get this red. Now, what do this red forces? It forces all the other people to assign blue. So is it a proper coloring? Is it the coloring of this graph such that every edge has got monochromatic, like non-monochromatic colors, right? So for every edge, you can check, right? So this is an algorithm. What is an algorithm? We started with one vertex, right? We gave it a color and we gave all its neighbors the different color. Then we try to propagate this color. This is like a flooding, right? Like you flood with red, blue to its neighbors, right? So is this algorithm clear to you? Let's see what's there. You want to try this again on this graph? So I gave red, I gave blue, I gave red, I gave blue, okay, and I gave red. So it's possible to flood and do this kind of coloring on this graph. Okay, so
Sir, I have a doubt, sir. So how you gave the red to these
the first
end
vertex.
points?
The
No,
first
sir.
vertex.
At the last one, the end, there are two reds. There
So
were two
first I gave it
reds.
red, right? I started with an arbitrary, doesn't matter, okay? Then I gave to its neighbors blue. Then I gave the neighbors of blue red, right? Then I gave the neighbors of, right, blue, right? Now, all these four vertices are neighbor to some blue guys, right? Look at
But
all
sir,
the remaining.
then both the last vertices will be red, and they both are neighbors of each other, so they can't be red.
Yeah, so that's where I'm
Okay.
coming, right? This is exactly what I'm coming, right? So we try to propagate, right? And now notice what happens. If I took this coloring, it forces us to look at this 1, 2, 3, right? Now look at the four guys. They must get red, right? But if I give them red, then there's a problem because someone should get blue. What does that imply? It may be that not all graphs are possible to color in this way. You understand what I'm saying?
Sir,
Right?
so basically this graph coloring is a bunch of permutations and combinations of like the different configurations we can have of a graph coloring, and that there are some configurations in where we will end up with colors which are connected and violate our condition.
That's right. Or in other words, it is not possible to color them with just two colors, maintaining the property that if you look at the endpoints of an edges, right, they will get different color. It is not possible to do it with two colors, right? But example, if I had third color, then at this point of time, I can give third color to all the four guys and we are done. We are happy. Because now, right, we were talking about red and blue, but maybe if I introduce red, blue, and green, maybe we can do this, right? So what it means is that some graphs, it is possible to color them with two colors. Some graphs, it is not possible to color them with two colors. And this is what is called coloring question, that you're given a graph G and your objective is to color the vertices with as few colors as possible, maintaining the constraint that if you look at any edge, endpoints of that edge should get different color. So this is a famous coloring problem in computer science, in graph theory, graph algorithms, everywhere. So what is the question? You're given a graph G and you want to assign colors to vertices and you want to use as few colors as possible, maintaining a constraint that if you look at any edge, the endpoint of these two edges should get distinct or different colors. Okay? Is that fine? Okay. So now notice that whatever I try to do this particular graph, I am not able to do with two colors, right? Maybe because look at, there's an edge and both have been assigned red, right? Now let's focus on this little graph. Okay, let's just focus on this little graph, right? Do you think it is possible to color this little graph with two colors? Think of any color with these five vertices. Can you really think that you can color them with two colors? So the point is, what is the point is that if you look at this forms a cycle, okay? How many nodes are there in this cycle? Or how many vertices are there in this cycle? 1, 2, 3, 4, 5. Now you can show that any odd cycle, any odd cycle needs at least three colors. Okay, any odd. And yes, hello. Okay. Okay. And so what we just now did is what is called an algorithm. We found a way, right? We found a way to color our graphs. What we started with, start with an arbitrary vertex, color it, give it any color, propagate its color to its neighbors, red. If you started with red, then blue, so on and so forth. This is an algorithm, not a logarithm. So first of all, okay, let's not get confused with algorithm and logarithm, because whenever I was young and people used to ask me, what do I work? When I used to go home, they will say algorithm. And invariably, by the time it reaches the third person, he says, oh, he works on logarithm. So it's like, okay. So let's not, at least this is what my mother did to lots of people. So I'm like, now I'm very careful that this is an algorithm, not a logarithm. Okay. Okay. So what is the property of an algorithm? Always outputs correct answer. So whenever you make an algorithm, you need to prove that your algorithm always outputs correct answer. And the algorithm that we described uses time linear in the size of the graph. What do you mean by linear in the size of the graph? So amount of operations, amount of time you ask questions is proportional to the number of vertices and the number of edges, right? So if it's linearly proportional, then it's a linear time. If it is quadratically proportional, then it's quadratic time. It's cubically proportional, it's cubic time. If it is exponentially proportional, it's an exponential time. You know, so what is the notion of time is basically how much amount of operations. Okay. Okay, so what is the notion of time? Time is basically when you see people say, oh, this algorithm is fast, that algorithm is fast. So what is the time? Time is number of operations that you did. How can you quantify that? Oh, the number of operations is linear in this size, quadratic in this size, cubic in this size. So if it is some polynomial, you will say, oh, it is taking polynomial amount of time. But if it is an exponentially in the amount of operations we do is exponential in the size of the input, then it's, oh, this is an exponential algorithm. You understand? So, and now linear is of course better than quadratic. Quadratic is definitely better than cubic. N log n is definitely better than n squared. So this is how you compare time of your algorithm, right? So what is the time you make an algorithm, and how do you say that this is the running time of my algorithm? It's basically look at the number of operations that an algorithm performs on your input, and is it linear in the size of the input? Is it quadratic in the size of the input? Is it cubic on the size of the input? So depending on what this is what is known as running time of the algorithm. And now once you have two numbers, two functions, you can always compare and say, hey, this is better than that function function is better than that function, and this is what is the meaning of I have designed an algorithm better than that algorithm. Okay, again, maths comes into play. Sometimes you really need sophisticated maths to prove the really what is the real running time of your algorithm is. Okay. Okay, so what is the meaning of this? Doubling the size of the graph means doubling the time the algorithm uses, right? Mostly, okay? Yes, this is the meaning of order n, nothing more, okay? I mean, okay, again, not maths, mostly, okay? Okay, so now we move to a three coloring. Okay, so what is the three coloring? Okay, so we have to color the vertices red, blue, or green, okay? And such that all the edges, okay, have different colored endpoints. Do you think we can do this? Let's try. Red. Now, I could have given this guy blue or green. I decide to give blue. Other guy, look, even this guy could have been given blue. I decide to give it green. Look, I have two choices. Either I can give the adjacent neighbors blue or green, or the Other guy, again, blue or green, I decide to give one blue, one green. But notice, once I fix blue, other guy I can give, this guy I gave red, or I could have given also blue, but I gave red. But the moment I gave red, this guy has a choice, left is only blue, because already two of its neighbor has been assigned green and red. Then this guy gets green, that guy gets red, that guy gets green, and now we are stuck. Do you see we are stuck? Because look at these two edges, right? Look at this remaining guy. One guy tells him to get red because he has a green neighbor and a blue neighbor. For the other guy also says, okay, you can only get red neighbor because you already have a blue or a green in your neighborhood. Okay, so basically we fail. So why did we fail? There are two reasons we failed. A, this graph cannot be really three color. That's the reason why we failed. Or B, we made a wrong choice. No. We are only allowed to use three color for now. We just want to say the following, answer the question, right? That, hey, this graph, it is possible to do with three color. It is not possible to do with three color. You need more than three color. That's all that we want to answer. We do not want to find the minimum number of colors at this point of time. All we are trying to say, okay, that's all, okay? That either this graph can be three colored or this graph cannot be three colored. So there are two reasons this graph cannot be three colored. It really needs more than three colored, then that's right. Or B made a mistake because we had some choices to make and we made some wrong choices, right? So let's make a second attempt. So when it is red, I gave that guy, both guys blue now. I could have either given blue. Now let's see. This guy gets red. Then once you have given, look at a triangle. Any triangle must get all the three distinct color. It has no choices because you can't color a triangle because it's an odd cycle, more in two colors. So I gave green and red. Okay. So now the moment I give this color red and the green, the other color, other vertex, hello, can I hear me?
Yes, sir. Now we can hear you.
Now can you hear me?
Yes, sir. I guess the connection is back. Yeah. Please, sir.
Yeah, it's like, it has rained a lot. So hopefully. So when you are not able to hear me, just put 0 in the chat. Then at least it will make me aware. So what I try to tell you that for the same graph, we made one attempt and we failed. We made another attempt and we succeeded in coloring in a way that every edge gets distinct color. One red, one green, red, blue, right? Or green, blue. Yes, do you have a question? I'm not able to hear if then please write it in the chat. I'll try to answer that. Or at the end of the talk, we can take every question and try to answer that. Okay? Okay. Okay, so what does three coloring meant? Right? In three coloring algorithm, we had to make a decision. Okay? In two coloring, we never had to make we had to make a decision and see the effect of decision much later. Okay? But in two coloring, what happened that we started with a color, gave its neighbors a different color, so on and so forth, right? But in three coloring, we had choices to make in the beginning. we made some choices and we saw that, oh, we made a wrong choices, right? If you notice, right? Remember, we made this blue and green and we saw later that this cannot be extended. So the choices we made much early, but it saw its effect much later. But this is what I mean to convey when I say we had to make a decision and see the effect of decision much later. One was right, the other one was wrong, right? So there is a choose, right? What is the choice? Either study maths or play cricket. Oh, maths, and after a long time you realize maths sucks, should have studied computer science. Sorry. Or you play cricket and after a long time you see that you succeed. So like, you know, in life we have to make choices and see its effect much later, right? So yeah. What happens if you have to choose twice? Candidate H or candidate T? Okay, and so you made a choice with candidate T, and after a long time you realize choose nuclear war or environmental disaster. Oh, nuclear war is not nice. Oh, environmental, disaster is not too nice too. Okay. Oh, all right, you choose H, then you have to choose football or cricket, success, lucky. So what I mean to say that more choices you have, like more complex the world looks like, okay? So this was an unlucky choice. So what was the 3 coloring? We had many decisions to make. First vertex, okay, is fixed, it doesn't matter. But now for the second vertex, for the first vertex, how many choices does it have? It could be either colored red, it could be colored blue, or it could be colored green. For the second vertex, it could be colored red, blue, green, so on and so forth. Third vertex, so on and so forth. So how many choices do we have? For every vertex, we have 3 choices, red, blue, and green. So if we had n vertices, then we could try 3 to the power n different colorings to try, right? So while for 2 coloring, it was like a linear time algorithm, as you said, or we gave an algorithm which was linear in the input size. If we really want to give a correct algorithm for 3 coloring, it might end up that we might take 3 to the power n. So previous one was so polynomial. This is exponential. If we have to try all possible colorings and check which coloring is valid. Okay? Is that fine? How bad is it? Okay? So let's see how bad is it. N vertices and running time, n and 3 to the power n. And suppose the number of vertices are like 10, 20, 30, 1,000, right? 10 nanoseconds, 20 nanoseconds, 30 nanoseconds, 10 microseconds, 1 second. But for 3 coloring, 600 microseconds, 34 seconds, 1 day, and even for 1,000, more than the universe lifetime. So that bad an algorithm of 3 power n versus n could mean for us. You see the difference? Okay. But now you might ask that, are there a smarter algorithm for 3 coloring? So David Epstein in 2000 is a very famous computer scientist. He made an algorithm for 3 coloring using 1.33 to the power n operations, which as far as I know is the best known algorithm up until now. Okay. So now let's see running time algorithm again with smarter algorithm. Again, slightly faster, 1.160 nanoseconds, 3 microseconds, 41 microseconds. But for 1,000, yeah, this also doesn't work. It's universe lifetime. Okay. So now, what is lessons learned? The function of the running time matters, right? How good algorithm you make is an important aspect of algorithm design. Okay. Exponentially.
I have a doubt if you can answer, sir.
Yes.
Sir, like in the linear, when we choose one color and the color of the next node was decided by that color only, right?
Correct.
Because they have to be different. Now we have 3 colors. So if I have chosen the color for one node, the node connected to it can have either of the remaining 2 colors, right?
That's right. So it is, you can actually show that if the graph is connected, the running time is 3 to the power 3 into 2 power n number of possibilities. You're perfectly correct.
So you said 3 to the power n.
Yeah,
It
but
should not be 3
no,
to the power n, right?
yeah, but then now you're trying to be a bit more applying some new idea, right? Okay, if I'm connected, I have small choices, but I said in the worst
Because
case, yes,
approaching
you're right.
this previous problem same way, we will have 2 to the power n, but
That's right.
we don't. Yeah.
But that will not matter because I told you that the smart algorithm runs even faster than that. See, 1.33 to the power n. Is that right?
Mhm.
But you're right. You're absolutely correct. You can show that number of valid choices if the graph is not, if the graph is connected, is 3 into 2 power n. If graph is connected. If not, then depends. Okay?
Can we do it in linear time and space using BFS?
We'll see in a minute.
Sure.
Okay? So open problem. Does there exist an algorithm for 3 coloring that uses 100 n operation, 100 n square operation, 10,000 n to the power 100 operation? Now, does that answer your question? That BFS will not work?
Yeah, yes, sir. Thank you, sir.
Good. Okay. I only have 18 minutes and many more slides. So let's go. Okay. So there are 2 possible explanations for that. Okay. No fast algorithm for 3 coloring found so far. A, no one has been smart enough, or it doesn't exist. Right? Now, we are mathematicians, right? So we like to believe this, it doesn't exist. Okay. So now, just to, how did we go about proving this? Let me give you an example with vacuum cleaners. Okay. So your boss wants you to make a vacuum cleaner and he gives you some particular specification to make this vacuum cleaner. You know, like a vacuum cleaner should have this ability, vacuum cleaner should have that ability, so on and so forth. Okay. Is that fine? Am I audible?
Yes.
Yes, sir. Yes, sir.
Okay.
You're audible. Yes, sir.
Fine. Okay. Now he has a very bright friend in Selden and he goes to Selden. He says, he tried to make this vacuum cleaner. He didn't succeed. And he goes to this Selden and he says, hey, can you help me make this vacuum cleaner? And he thinks for a while and says, I don't know how to make it, but I have even more smarter friend. Let's go and ask him. So, and whom does he go? He goes to Einstein. Einstein thinks for a while and he says, he's a very smart person. So he thinks for a while and says, okay, actually, I also don't know how to make this. But he says, look, if we can make this vacuum cleaner, then it will imply that we can make time machine. You know what is time machine? You can, okay? Or we can make this, what is that called? You know, unicorn bunny.
Yeah.
And this is cold fusion. Or we can travel faster than time, right? So what does he say? Look, if you can make this great vacuum cleaner, then you can make all these mythical objects, which is very hard to achieve. Okay. So now it is up to us to interpret this answer. Okay. What is a pessimist would say that it probably means that such a vacuum cleaner probably does not exist. And what will optimists say? Oh, let's forget about everything else. Let's put all our mankind and all our efforts in making this vacuum cleaner. So it's up to you to interpret this answer all the way. Okay? Is that fine? Now, why did I talk about this vacuum cleaner example? Because for 3 coloring, here are the 3 famous people. Okay? They are basically Karp, Levin, and Cook. And what did they say? If you made that amazing fast algorithm for 3 coloring, then you can make this time machine, unicorn berry, all these amazing things. Okay? So if time machine is not possible, then fast algorithm for 3 coloring is also not possible. Okay. Anyway, so not actually, this is not what they showed. Basically, what I'm trying to tell you that, if you're able to design such good algorithm for these things, then you will be able to design some amazing objects which we do not believe that they exist. Is that fine? Okay, but what they showed is that verifying solutions. If I gave you 3 coloring and ask you, hey, can you check whether this is the correct solution or not? Can you do this fast? What I mean by this, I gave you a graph and a 3 coloring, and I'm asking you, hey, can you check whether this is a 3 coloring or not? Meaning, can you go and check for every edge whether they have got both endpoints has got same color or different color? Look, when I asked you to find a coloring, that's a hard job. But when I'm asking you to check whether this is a 3 coloring or not, it's a much, much easier task, right? One is about coming up with a coloring, other is verifying if this is 3 coloring or not, right? So do you understand the magnitude of these two different questions? One is about verifying, other is about coming up with a solution, right? So coming up with a solution is always harder than verifying the solution. Okay, so I'll give you a very good example for this. So when I became faculty for the first time, I used to give people tasks which I could only solve. Okay, but one day I realized that do I really need to give problems to people for assignments and like exam which I can solve? I don't need to solve this. To correct the question paper answer set, all I need to verify is that the answers are correct or not, right? So you will agree to me that verifying whether the answer is correct or not is much, much easier task than coming up with a solution, right? So as a teacher, this is the greatest advantage we have. We can give you any question, even when I don't know how to find an answer or how to do that, all I need to do is to verify your answer, and that's easy because, I mean, you understand that, right? So for example, you don't know the answer, but you can definitely go and find answer on Google and verify it and write it in your answer sheet, right? That's much more easier job, right? So this is an analogy here, is that verifying answer is much, much easier than finding an answer. Okay, so can efficiently check whether a proposed solution is correct or not. Okay, so it is easier to verify whether a solution is correct than it is to find one. Okay, right? We all agreed to this. So what did these people tell? They told that fast algorithm for 3 coloring will imply all computational problems that one can check solution for quickly can also be solved quickly. Do you understand what they're saying? That look, if you can make such amazing algorithm for 3 coloring, then all the problems for which you can check solution faster, you can also make algorithm, you can also find such a solution faster or easily, right? So you do understand what is the veracity of statement these people proved? They prove that look, verifying is equal to finding if you can give me such an algorithm, right? So this is why we don't believe, because we believe at this point of time that coming up with solution is much more harder than verifying one. We don't believe that for 3 coloring we should be able to find fast algorithm. Okay. Okay, so okay, I have still some 10-15 minutes. I will entertain you. Let's see. Hopefully we'll finish quickly now. Okay. Okay, so I hope you understood the message of these slides. Right? What is the message of this slide? That there are several computational problems for which we do not expect to find good solution because A, we can verify it easily, and if we can find a good solution, then there will be a good solution for almost every computational problem. Yes, I mean, as I told you, right? I'm only talking in a very general sense. Of course, there are problems of different kinds, and they have different setups, and we have to be careful with respect to that. But like, let's say it's like a pop talk, like popular talk. So popular talk, we can believe that many things do not exist. Okay, I want to give you another example. Yeah, in most cases, it is always easy to verify. In most cases, but there are also here. For example, I give you factoring, right? Finding factors are hard, but given a factor, you can multiply them easily and check whether it is factorizing or not. It is, right? Sudoku. If I ask you to look at the factoring, right? Verifying is easy, finding is difficult. Sudoku, right? Here's one example of Sudoku. Finding a Sudoku, making Sudoku is difficult, but if I fill these numbers, you can easily verify whether they are correct or not. Similarly, like in planning and like in traffic and this, that, everywhere verifying is much more easier than finding one. Okay, and so for three coloring is not an exception. What they sold, that far seldom for long list of problems, like all these problems that we just now spoke about, if any of them has a solution, that will imply all computational problems that one can check solution for quickly can also be solved quickly. And this is a P versus NP question for which we have Clay Institute has put Sismat prize. I'm not even going there, so maybe $1 million. Okay, and this is one of the famous mathematical question for which we still do not know an answer, among few famous mathematical question for which we do not know the answer. Okay, but what is P, what is NP? Do not worry, right? But whether three coloring has a polytime algorithm or not, without making these kind of assumptions, is what P versus NP question is. Okay, so the world of computational problems so far, problems that can be solved efficiently, two coloring, problem for which a solution can be checked efficiently, and if one of these fast algorithms, if one of these has fast algorithms, then they all do. This is like three colorings here, right? So people ask, is anything out there outside this? The answer is yes. Like factoring is there, for which we do not know, like we still do not know whether it has an efficient algorithm, or if we get a good algorithm for factoring, then all algorithms will imply factoring like has a good algorithm. We do not know anything about such things. So we do not know, like, of course, factoring belongs to like this light blues. All we know that we do not know whether factoring is belongs to this dark blue or like this rectangle or a circle. But what about on a quantum computer? But if we have been given a quantum computer, not a classical computer, then we can show that factoring belongs here. Okay, and then with the also notion of some sort of randomization, then that is also supposed to be slightly larger than one which we can solve without, without using some randomness or without using dice. Okay, and we do not know anything belongs here or not. I mean, we still do not know whether the bigger rectangle is equal to a smaller rectangle or smaller rectangle is properly contained inside bigger rectangle. We still have not answered some of these questions yet in computational world. We don't know this. Okay, I don't know anything about quantum computers. It's like very popular science, quantum physics. Okay, don't ask me any question about quantum physics. I have absolutely no idea what quantum physics is. Okay, okay. So that's all that I know. So quantum allows stuffs to be in two places at once in a very spooky way. Here is literally all that I know about quantum physics. That it allows stuff to be in two places, at once. So suppose you have a photon gun. So this red thing is a photon gun, okay, that shoots one photon at a time, and you set up splitters and mirrors as shown in the picture. The splitters are such that 50% of the time photon passes through them, and 50% of the time it photon turns. Okay, so this is how the property of this. So the possible paths. So the photon is both on path 1 and path 2 simultaneously. Okay. Okay. So I mean that's all. So the possible paths are this gray ones. Right? So either it can go up and this, or it can go and be detected. Okay. So if you put up two screen, okay, so if you put the two screen simultaneously immediately after the first splitter, we see 50% of the time the photon hitting one screen, and the 50% of the time hitting one screen, half the time the other. Okay. So far there's nothing spooky about what I said. Behavior of photon is deterministic. We just can't predict precisely which side it is going to be. But at least this is what I thought, that if we know that 50% of time it goes in the one direction, 50% time it goes in the other direction, then if I put detector, and then 50% time we should expect a photon here, and 50% of time we should expect photon here. But that's just wrong. Okay. Because if that was the case, then even after the second splitter as shown in the figure, okay, we should see the photon hitting each screen half the time. What actually happens in experiment is that photon always hits the top screen, yeah, this one, right? Although we believe that 50% time, it should be detected here, 50% time detected here, but in experiment, mostly it is detected on the top. So I really don't know. So what is quantum choices? It's like quantum choices, like if you look at 3 coloring algorithm, quantum choices like you make first vertex, second vertex, no. It's not like this. Very, very misleading. This is not how the things are. It's like quantum choices are somewhat less misleading. They're like some sort of, I don't know how to say that. Let me say what I want to say. But the quantum really looks like is that you don't make all choices at once. You make a weird quantum soup of all the choices at once, and you need to pick out from the soup the ingredient that corrects to the correct choices. Okay, so so I really don't know. So there is some notion of quantum computers, which is basically a weird mix of quantum choices, and you pick the right ingredient in a particular way. What is known is, okay, factoring has an efficient quantum algorithm, like in the sense we made, like polynomial algorithm for factoring on quantum computers, and quantum computers almost don't exist yet, but we don't know in the future. Yeah, you also don't have to understand anything. Okay, all I'm telling you, this notion of some quantum computer where choices are very, very weird. Okay, and on that weird computer, you can make factoring efficiently. Okay, that's all. So is that fine? So what I'm saying, quantum computer is a weird computer where you can have exponentially many choices, but the choices are chosen in a way which is very weird, and it can solve my factoring problem efficiently. So in that sense, correctly, quantum computers are slightly more powerful mathematical object than the classical computer, but not much. But they still don't exist yet. Okay. If you want to know more about quantum computer, go to Scott Aronson website. You will know way, way more than what I just absolutely don't know much. Okay. So let me see what's time is like. Okay, so there's also a notion, of randomization in computer science, is that, you basically, at any point of chance, you have several choices. You make a choice by just, doing you randomly choose one of the choices by, throwing up a dice. And we ask ourselves, if we allow you this power of randomization or with dice, can you solve more? Well, so what is with dice versus without? So algorithm takes an input and it gives you an answer. This is okay. But now what happens to dice throws like this, and you give an answer correct with some probability, or you give an answer wrong with certain probability, right? So the difference between an algorithm with randomization or without randomization is always you give an input, it gives you answer yes or no correctly. But when you are allowed some amount of randomization, that okay, you have several choices, make one choices with probability proportional to something, okay, then what happens is that you can give a correct answer 99.999% of the time, and you can give wrong answer 0.0001%. So we are aware that this algorithm gives me correct answer, not always, but mostly. So these are the properties of randomized algorithm. Okay. So it's like a hay in a haystack. These randomized algorithms work in a framework of hay in a haystack. We can't find it blindly. So I just wanted to give you some overview of something that people do in computer science. There is notion of randomized algorithm, there's a notion of quantum algorithms, and then absolutely amazing notion of deterministic algorithms that I have spoken about 90% of time in my talk today. Okay, so this is how the world looks like. So here are some concluding thoughts that I would like to make. Okay, optimization is ubiquitous. Like optimizing something is like everywhere. Like sipping, like some color and this fire everywhere. Optimization is all around the place. And most problems are NP hard. No algorithm solves. What is the meaning of NP hard in pop sci culture is no algorithm can solve all instances optimally in polynomial time. So how do people cope with hardness? Well, you restrict input. That's one way. Or parameterize algorithms that I do all my life. You forget about solving the problem optimally. You say, look, okay, I can't find best solution. Can I get closer to the best solution? And that is what leads to approximation algorithm. And you say, maybe I can't do in polynomial time, but maybe I can do in exponential time, right? So this is how you look at every aspects of these hard problems, and you try to design algorithms for these problems either by restricting input or forgetting optimality, not trying to solve it exactly, but solving approximately, or foregoing the polynomial time design and saying, okay, let's do it in exponential time, so on and so forth. Okay, let's forget it. Conclusion, we don't know much more than we know. So thank you for listening to me. So I hope last 5-10 minutes was supposed to be your, just to be make you believe that there are more to the world than I just spoke about. Okay. So I talked about quantum computers. I talked about some randomization, blah, blah, blah. If you have interest, you can go and check this terminology on web pages and you will find them. Okay. So now I'm open to questions, criticism, anything you ask.
Hello, sir.
Yes, please, suit.
Sir, in the middle of the presentation, there was a term, sir, NP versus N.
P versus NP.
Sorry, P versus N. So can
That's
you
right.
elaborate something more about on this?
Oh, can I say something more? Okay.
Yes.
So what it P means? P means basically all the problems which on your computer you can solve in time. Input size to the power some constant, like some polynomial. Okay. And NP means for all those problems for which we don't know how to find solutions exactly or correctly, but if you give me a solution, I can verify them easily. You understand my point? So polynomial time are those problems for which we can efficiently solve it. NP is all those problems for which efficiently we can verify it. Is that fine?
Yes, sir. Fine. Understood, sir. Thank you.
Yeah. So P means efficiently solvable. NP means efficiently verifiable.
Okay.
And by efficient, I always mean time which is polynomially proportional to the input size. Okay. More questions.
So, Shreyansh here. I wanted to ask that once I listened somewhere that there's a bound on sorting algorithms that they can't perform better than log linear complexity unless it is counting sort where we give extra space and it solves in linear time. I mean, there we can statistically have some samples and we can converge to an idea where okay it has this much runtime or it has this much complexity, but uh, I didn't find any rigid mathematical proof where we can safely say that okay this is literally the bound where if we don't use extra space then okay log linear complexity is the bound.
Log linear. Okay. Wait. There are a few things. First of all, when we want to prove something mathematically, we need to talk about the model. Okay. A. B, we have to talk about the running time. Okay. So what is the running time of an algorithm? So running time of an algorithm is basically what we do. Imagine that I look at all inputs, or imagine, let's say sorting. I look at every n size input or every array of n size, and I say, what is the worst n size, like what is the worst running time on this n size input? Okay, that is my running time. So these are basically pessimistic algorithm or worst case analysis of algorithm, right? So I'm not talking, it's not the average case analysis. I'm saying among all the n size input, what is the worst I can take? You understand my point, students? Okay.
Yes.
If that is my model of computation, then, and the only thing I count is how many times do I compare, right? Then I can show to you that you at least any algorithm need to compare n log n times, right? That's one thing. Okay. But now there could be average case complexity. What do you mean by average case complexity? That imagine that I look at n size input from, and I look at this n size input from some distribution, like some probability distribution, right? Now, I find the running time of this, but what is the probability of finding that particular that particular input, right? So I also have to multiply that, right? So if I sum over these running time, then that's an average running time of my sorting algorithm on this. For example, quick sort on an average, whatever that means, takes linear time.
So one question.
Yes.
So what is more demanding in AI? Is it computational power or the quality or amount of data?
Everything is important, right? Look, I'll give an example where you're going to use it, okay? Suppose if I'm going to use machine learning algorithm in airline industry, right? Who's going to make decision about whether like some critical components in airline industry or flight. There, what is more important? Both, you need to do the computation very, very fast, like optimization to make a decision, and also correct decision, right? Right? But in some situation, we care about much more quickly and do not care about that more efficiently. You understand my point? So based on what is your relevant domain it is, based on domain, you need to decide whether to go for accuracy or I go for efficiency or computation. You understand my point? Or I need model of both, right? So I can't expect we can't expect to apply, maybe we apply slightly slower algorithm, but if it comes up with a correct decision much more often, then maybe there will be domain where that would be preferable compared to I need to be fast, but I'm aware that I might make mistake. You understand my point?
Yeah. Can't we not look for a perfection and stop at certain level of quality?
We could, but again, it's a domain specific, right? Why do you see that? Like machine learning is very domain specific at this point of time. Medical industries apply machine learning in a different way. Transport industry apply in a very different way, right? Because the kind of questions that they are trying to optimize is very input sensitive. Okay, so based on what kind of data I'm trying to analyze, so we have some general methods, okay, which we do not care about. We say, oh, if data comes, this is. But now if data comes from medical industry, that might have some correlation among them. If data is coming from airline industry, they might have some correlation between them, which we would like to exploit. You understand my point, right? So we can take these classical algorithms and make them sensitive to what my data is and make it much more efficient or make it much more whatever, by utilizing the properties of that.
Okay, thank you, sir.
Welcome. Yes.
Hello, sir.
Yes, please go ahead.
First of all, thank you so much for your thought-provoking, talk, especially for somebody who is naive about, algorithms and all. So I come from a biological background, but I do have some engineering background too. So my question is, if you are working on developing an algorithm, specifically say not for purely mathematical problem or computational, but say biological problem.
That's right.
Could you suggest something like any basic principles as to one should keep in mind while you are taking the first steps, the first baby steps when you are trying to develop an algorithm? That's a basic principles, if you may.
Okay. So first of all, there are several things that several things that work well in is what I call heuristic. Okay. So one thing that you should always be, whichever domain it is, to come up with what is the problem that you want to solve, right? What is the notion of data and what is the problem that you want to solve? Once you're able to come up with, you have been able to formulate the question that you want to solve, okay, automatically some set of heuristic will come into your head. You understand what I'm saying? Okay. The reason why we make mistake many a time, I'm not talking about efficient algorithm, mathematical algorithm, is that what problem that I want to solve is that itself is not clear to me. You understand the point? So many times when we have a conversation with interdisciplinary people, right, the first thing that we talk and discuss is try to understand the other person and come up with what is the problem that you need to solve for your domain or for your problem. You understand my point, right? Once you have this, you can come up with lots and lots of heuristic. You don't have to worry about always the mathematical framework, right? I'll give you an example of heuristic, right? What we did for the coloring, right? We started with one color, gave all the other guy. Like, isn't it very natural to come up with? Like, this is how we should be doing, right?
Yes.
Yes. But what was more important? The question. right? The moment I write my question very properly, that this is given this input, this is the output I want. And what is the problem writing? Hey, this is what my problem is going to take, and this is what it should output. Input, output, input, output. Once you're able to write that properly, trust me, in your head, lots and lots of heuristic will start coming in. So the difficult task is write what is your problem going to take, or what is your algorithm going to take as an input, and what it is going to take, what you call, give you out as an output. If you are able to do that properly by understanding, by talking to each other, okay, that's already great. So that's the first thing you should always try to do. What is my input and what is my deliverable? What is my output of this algorithm? Okay.
Okay, sir. Thank you. So just a quick follow-up question. So one
Yes.
thing I have always faced the problem is versus, specificity versus generalization. If I'm thinking about solving a problem or coming up with an algorithm, how should I think? Should I think that solve this problem specifically first and then think of generalizing, or should I think like top down, think about a general solution and then try to, bring it down to the specific?
This is very people specific. Okay, some people like to think general to specific, but like whatever works for you. Since you do not come from computer science background, my suggestion would be that you go bottom up. Like you try to solve on some of the instances. As I said in the beginning, right? I generally write for some hypothesis, write a program and check how does it work on small inputs, right? Like some 10 vertex, 15 vertex, right? You can also do that. That is exactly like writing something on small instance, right? Like specifics, right? And from a specifics going to generality, right? So I'm looking for some pattern in these specific examples to come up with generality. So this is also a perfectly valid method.
Thank you so much. Thank you so much, sir.
Anything else?
Sir,
Okay.
may I ask the question?
Please go ahead.
First of all, I would like to thank you, sir, for taking this session. It was really insightful, and it helped us explore many different aspects of mathematics in computational programming. So my question is, it is actually something out of curiosity. So we all know that the fast Fourier transform algorithm was designed, like the credit goes to Cooley and Tukey. So they designed the algorithm, and it became a vast success in being able to detect the underground nuclear tests. So that's how that usage of the fast Fourier algorithm made them both famous. But later on, it was realized that Carl Friedrich Gauss had already found that algorithm and written in one of his books. But due to language barrier and due to it not being popular or not being useful that time, somehow people did not realize that. So I wanted to ask is, are there such examples in the field of computational analysis also? Like, for example, in the 20th century, some researchers might have found a very fast algorithm to solve a problem, but somehow people did not really need at that time. And now, since the computers have become faster and faster, they have still not really needed them.
Yeah, these things keep always happening, like imagine yourself some 25, 30 years back when internet was not there, right? Imagine, especially look at lot of science which happened in Russia was very local, okay? And they already discovered many of these algorithms which West discovered and everything, but these people only published in local languages and this. So these kind of language barrier, as well as, world was not so open. Like, for example, I don't expect now that something will happen now in some part of the world and it will be hidden from the world. This might not happen. But in the olden days, this happened so many times. So yeah, like a lot of even linear programming algorithm, there have been several algorithms that people have rediscovered in parts of the world, and people didn't know that earlier also it existed. So yeah, this has happened several times in history, and it keeps happening even now.
Okay, sir. Thank you, sir.
Yeah, so thanks. I think we'll have to end the Q&A session here. So thanks a lot, Professor. On behalf of all of us here, I would like to thank you for this excellent talk. That too on such a short notice. So I think a lot of complex topics were presented by you in a very accessible manner to all of us. I think it's a very insightful talk, especially given the audience that we have here. So thanks a lot again, and thanks for accepting our invitation.
Thank you. Okay. Good luck. Bye-bye.
Bye, sir.
Thank you
Thanks.
so much.
Thanks a lot.
Saket, I'll just take your 2 minutes.
Yes, please
If
go
you
ahead.
don't mind. Yes, so thank you, Karthik, sir, for thanking Saket sir on behalf of IITM. And sir, just one small request is that the instructors, the mentors of our IITM based degree and the core committee wants to take a screenshot with you.
Sure.
Is that possible?
Yes, perfectly possible.
The technical team, Nishkar and Jai, please look over it.
Yeah, sure.
Yes.
Okay. What do I do? What do I stop?
Is it good to go, technical team?
Just a second. Yeah, works.
Thank you.
Just a second. We are taking it. Nishkash, also, can you confirm?
Yes, it has been taken.
Saket,
Thank you,
sir,
everyone.
may I take a minute, sir? I just need to ask something.
Please go ahead.
Yeah. Sir, like I'm a student and currently we are in learning phases and looking at the volume of material that we have to learn because it's not such a small thing. Sometimes I'm like overwhelmed by it and the uncertainty of not knowing the answers when we are trying to go through the problems. So maybe you can advise something on learning mathematics basically. When we are grappling with so many problems and trying to solve so much problems and I'm not most of the time able to handle the uncertainty that I do not know. That pain that we are psychological pain basically that we have to go through.
I
Maybe
can
you
just
can
share
put.
a anecdote. Okay. So when I started to learn mathematics after my high school at CMI, it was very different kind of mathematics that I had actually seen while in high school, like numbers. And suddenly you see proofs. They like maths look literature, then the maths itself. I hardly saw numbers. Okay. So it was a decision that I had to make. What should I do? So it is always a trade-off between depth versus breadth. So what happens is the most curriculum tries to, at least in India, tries to teach us breadth rather than depth. Okay. And as a person, I was very unsatisfied if I learned something and I did not like there's a learning for the sake of learning, and then I learned for really knowing something. So every semester I realized that the 4 courses that I have to pass is impossible that I can learn deeply about every aspect of everything. I chose 2 subjects where I did depth first search. I went as deep as possible, and for 2 subjects I just did basic minimum, which is to get the course going in my life. You understand my point? But whether you can do 1 subject deeply or 2 subject deeply or 4 subject deeply is completely proportional to your own abilities that you have to make a judgment. That's one thing. Okay. And B, more importantly, what is learning? Okay, I'll give you a very good example that when I did a real analysis course in my 3rd semester, I barely passed, like D, out of like A, B, C, D. I think D or CD was my grade, which just meant at that point of time, I was not able to solve something. At the end of 3rd year, okay, I went back, more experience, and I picked up routine. There was hardly a question which I couldn't solve it, right? So when I did my real analysis course, I was not prepared for the science that was taught to me. But at the end of my 3rd year, I was prepared for all the science that was taught to me. So again, you want marks, you want grades, or you want understanding. Sometimes what happens is that we ourselves are not mature to take the subject well at that point of time. So you have to just wait for maturity. Sometimes we learn some other subjects and that other subject provides us maturity. For example, how did I learn real analysis? Because I did a course on approximation algorithm. Then I realized, oh, this is exactly what epsilon delta meant. And once I understood what epsilon delta meant, there was nothing in real analysis that you cannot do. Right? So it is all about understanding what that epsilon is and what delta is and how they relate with each other. Then tell me, is there any topic in real analysis that we cannot get inside and follow it up? So which subject can teach you what aspect of science or what aspects of mathematics is not clear? Okay. So but what, another thing which I felt very good about myself was that I used to get assignments. We were just second batch for CMI. So everybody was like, did their assignment by themselves, which meant that at the time, and they had 40% weightage. So there were times when I gave them assignment by just solving 30% and 40%. Assignment, it is not an exam. But I realized later that it's just a matter of time. I was able to solve the problem. It is just that I was not able to solve the problem in a week time, 10 days time. And that gave me a lot of confidence that, okay, mathematically I'm learning, I'm maturing. It's just that the time constraint that CMI has put for me to learn this subject is not optimum for me. So once you realize that you are learning a subject, it's a great feeling, and then you don't care about other things. Okay, I'll pass. If I will have a set of skills that I need to learn, I will be happy. I will be great. That's all.
That was amazing. So I must say the group of people who attended to today's lecture, they're not from core maths, they're from data science and artificial intelligence and such related domains. And how you explained, I think they really connected with you today. I would love to invite Dr. Shubhajit Chandra to say some ending notes to sir.
Excuse me.
Yes.
Is it okay if I ask one doubt? Sorry.
This is now on Meghna.
Okay.
Megha.
So my doubt was that I am actually looking towards a career in software development.
Okay.
The sidelines, I'm also studying this degree. So my question to you, because you are a research with like professional experts in research, how do you make a choice as to whether research in computer science or in theoretical mathematics is the place for you to be? Like, how do you make that choice? What questions you need to be able to answer to yourself?
Oh, that's a very heavy question. Okay. I don't know why I'm at this, like why I'm doing research. Okay. This question, I actually have no answer to it. Okay. Okay. So at least the kind of education I had in my undergrads, it was geared towards doing research. That was A. B. When I finished my undergraduate, I did not think I could get any job but to continue my PhD. Why? Because all my seniors were doing my PhD. So whether I made those choices based on more awareness or I made those choices by looking at other people is not very clear to me. Okay. So personally, okay. So I think it was the atmosphere which propelled me to go towards research. Okay. But there was one thing which was basic common. Did I love solving problems? Yes, I did love solving problems. Okay. Okay. So even at this point of time in my life and career, and like that's only thing that keeps me going every day is that am I ready to think for few hours on problem on my wall? Okay. And that's it. So if that is the kind of thing you have about solving problem in any field, go and do research in that field. Okay. And even when you are software developer or whatever it is, you can be researcher in your own domain, in your own way. Not everybody has to be in the research field to be researcher, right? Thinking is all about researching. Thinking is what I define research. And you have a problem in your field, nobody knows solution, you come up with something interesting, you come up with something solution, that's the research. So it doesn't matter, yeah, you are doing software engineering, you're doing this course, like if you like solving something, if that is what you want your life to be, then definitely do a PhD and everything. But you enjoy it more like a fun process, then do it on any way, no, that's okay. So, I mean, like researchers are basically, I mean, it's an overstatement. Like we all are researchers. I mean, we all are doing research in our own way. Someone is doing for money, that like me as a profession. Someone is doing it for fun. And so, yeah, just leave it that way. Okay. If that is what you want your profession to be, because this is what you want 24/7, then please go and do it. That's great. But just think about something every day, because God has given us brain, mind. We should think about it. And that is all that research is all about. Thinking on something new. Okay, this is what it is. How can I go and do something else? Once you are asking about these questions, that curiosity is all about researches. But that's it. I mean, yeah.
Yes, thank you, sir. Thank you, sir, for this inspirational talk and the motivation you have given at the end. Thank you for accepting our invitation.
Thanks,
Thank you.
Subhajit. Thanks,
Yeah,
guys.
thanks.
Bye-bye. Have a good day.
Bye.
And have good
Bye,
talk by
sir.
with you.
Thank you very
Bye-bye.
much.
Welcome.
Bye, sir.
Thank you,
Thank you,
sir.
sir. Thank you,
Thank you,
sir.
sir.
Thank you. Thank you very much, sir.
Thank you, all of you guys. And don't forget to attend our evening session. We have Dr. Ritu Bruto Munshi in the house. He will be joining us exactly at 6 p.m. And from 7 p.m. to 8 p.m., we have fun activity where we will be answering all of your questions, all of your doubts, and you guys can just take over the stage where you can just turn on your cam, unmute yourself, and it will be a very friendly interactive session. Shubhaji sir will be there with us. And so, okay, we are looking forward to a very productive session in the evening. Don't forget to join. Don't forget to subscribe the YouTube channel. Sorry, I think I should say like the YouTube video, right, Jay? And also
Yes.
don't forget to follow our social medias. Thank you, guys.
Also, we'll be again live from 6 to 8. We'll post the link in the chat itself. Please do join us, right? And we'll be joining to the same meeting link, right, Megha?
Absolutely, absolutely. It will be the same meeting link, but the YouTube link will be different. We will be sharing it, circulating it in the groups and in the social medias. Do not forget to follow our social media accounts. Thank you, guys.
Thank you. Thank you very much for joining, guys.
Thank you, everyone.
Thank you, everyone.
Thank you, guys.